u prime equals u plus the sum of the vi's, and 2 for every little l, we have that u plus, if we don't sum all the vi's, but we only go up to a certain point, and then we need this to be non-zero coordinate-wise. So, and we call, these are called so we go from, so the idea is we go from U, we can take some steps with vectors, and we never go outside of the positive, out of the non-negative numbers. And after a certain number of steps, which is capital L, we arrive at U prime. And we should be able to do that for every U and every U prime that can be reached in such a way. So indeed, maybe this is good to check that the U prime we require this to be in f of u, and indeed a of u prime will be the same as a of u, because a of all the vi's is always 0 because they live in that kernel. So this is
and also all the intermediates.
And all the intermediate steps
stay inside the prime.
Stay inside the non-negative integers. There's an alternative point of view which I won't write down because of time, but you can, for the fiber f of u, you can build a graph, and all the vertices correspond to the elements in f of u, and you put between some v and a v prime, you put an edge exactly if v minus v prime, or the opposite is inside this b, and then the sort of the word moves makes sense. And then saying that the set B is a Markov basis is the same as saying that the graph that you've produced in this way is connected. Because from U, you can walk to every U prime through. So the definition allows for the following theorem, namely, there exists an algorithm which, so my lemma was called lemma 1, so I'll call my theorem theorem 2, and namely the algorithm will be algorithm 3, so I'll give it straight after the lemma, that produces a sequence which is an aperiodic, reversible, and irreducible Markov chain. So I'll first finish my sentence, which has stationary distribution So maybe first.
You mean a conditional?
I mean the
Hypergeometric?
yes. So maybe stationary. Maybe as to say general hypergeometric distribution. Maybe first these words. So these are not relevant for today. By which I mean I won't go into them. I should apologize to Richard. Maybe you taught my first year probability course. I forgot what these are.
Yeah.
But so the function, I don't know what they mean, but the idea behind the theorem is if we run this algorithm that I'm going to give in a bit, we will generate some samples, the ones that we need.
I have to apologize too, because I don't remember either, but aperiodic and reversible are not contradictory.
I don't know, because I don't know what these mean.
It sounds like you can go there and then go back again. That sounds like a period. But maybe it's no non-trivial.
Maybe it is for afterwards or in a break.
I think aperiodic means that for. We should say what a periodic Markov chain is, and that's a Markov chain when, if you're in a particular state at a particular time, you can only be in the same state again at fixed periods thereafter. Like, it always takes 4 steps to get back, so you can only be there on the 4th or the 8th or whatever. And so a periodic Markov chain, which has the other, which is also irreducible, for large enough n, you can get from anywhere to anywhere in n steps. Don't have to sort of look at even n or whatever.
So I also want to give the proof of this theorem.
So if you have a Markov chain where you can stay where you are with positive probability, then it becomes automatically aperiodic because you can stay where you are for any length of time and then come back to other places later at any times.
So let me give the algorithm. So as input, we take some u in n to the r with some u I equals n, so that will be just our u given. And furthermore, the Markov basis for A, so maybe we should say we need to input A as well, the metric stuff, but it won't actually appear in the algorithm. But you need to know the background. And we need any probability distribution, which I will call phi, on f of u satisfying phi of u prime has to be non-zero for all and actually now on the spot I'm wondering can we actually do that, because it seems like you need to know the fiber filler anyway, so maybe that's not the main difficulty in calculating. And the output,
Even when you're calculating t might be hard. So,
yes,
and we don't.
and the output will be a sequence u1, u2, all of which line the fiber. So how do we go about it? Step 1 is we initialize u1 equal to u, and then step 2 is select uniformly random. That's really nice. For repeat. We need to select a random move vi from plus or minus v, and 2. So if ui plus vi is not always non-zero, then we non-negative. We set ui plus 1 equal to ui. So that means that this step that we took wasn't actually allowed from there, so we don't go anywhere. And otherwise, I will maybe self-fix the theorem just says that this algorithm works. And otherwise, so if the isn't allowed move, then we introduce some local variable, which is so this can be because this is not this inequality, so the non-negativity is not violated. This is allowed. We can set this, and the next one will be either the new one or the old one with probability q or 1 minus q. So that's a random step. And then in step 3, just to complete it, we output the sequence. And you'll notice that there's not actually a stopping condition. So we need to stop whenever we feel like it. And then there's the question is, how long do we actually have to continue? How many iterations are needed for the output sequence to be sufficiently close to what we need? And according to the book by Sullivan, this is an open research question in general. So the algorithm works after some time, but we don't know how long you have to run it.
So we know that it converges in the limit, but we don't know how fast.
Yes, we don't know how fast it converges. But at least we now should, if we are sufficiently patient, we have a way to sample from the fiber. So, and therefore, following the
Well, after we've run this for a long time, we hope Markov chain has reached the stationary distribution.
Yes. Right. Oh yes. And
then we pick one, and so we've got one item from the stationary.
Oh, and then you need to run it again.
Then you have to run it again a long time.
For a long time, and
to get again another one.
Richard, wouldn't it be smarter to wait for a long time and then take a fixed amount of the
No,
last
because you-
because at the end they reach the
No,
mark?
because you want to have a random sample from that probability distribution,
Oh, okay.
and if you run it for a long time and then take ones which follow one another, they will be close together in the same regional space. They definitely not independent because they only differ by these small steps. So you should wait a long time and then take one, and then wait a long time again, take one, and so on. And actually, we do know a lot more. We do know. I think a lot is known about how fast this converges.
Oh, okay.
If you go to the paper by Diaconis and Sturmfels, on which is Chatter's based,
And
you
his
will-
algorithm is
and
also
the
a
algorithm is
calculator.
taken from that paper, you will find quite a lot of information about the rate of convergence,
Okay.
and so lots of examples.
So, as I said, we have to reduce our problem a few steps, and so we have this algorithm. One might pretend that we're done, except that we need a way to test if B is actually a Markov basis. So that's the next new problem that we have, testing that B is a Markov basis. And I suggest that we take a quick break before we do that. Maybe 10 minutes or so.
When do you plan to finish, Erik?
I think one.
Okay.